Hey guys, hello, welcome to a new series, I guess. It's kind of late in the night and I don't know. I just had this random thought of trying to make a new video series on YouTube, trying to explain some cool new stuff. So I've been recently getting into data science, machine learning, and deep learning. It's a lot of technical things, but I got this cool idea of trying to make some videos, trying to share my knowledge and share my projects and share cool stuff that I find around for you guys to learn, for you guys to benefit from. Share some links which might help you, and also share my journey and in learning on my own. So this is I'm not doing any college degree in machine learning or anything like that. This is completely self-taught, self-learned, something that I did completely on my own, and I'm just still getting started, and I hope this process of documenting my journey would help me and help you as well. So, so my plan for this series is to basically talk about things that I do. So, if you haven't checked out, this is my website, realnihal.github.io. I'll make sure there's a link in the description, and there's a lot of cool articles. There's a little sneak peek of future videos. So you can just go through, have a read. It's not much. There's some cool articles. Um, so yeah. So today I wanted to talk about this project that I did. It's called FoodVision using TensorFlow. So for those who are not familiar with computer vision or deep learning in general, computer vision is a kind of problem in which you teach the computer to recognize patterns in images or videos. So in this particular problem or in this particular project, I'm trying to teach a computer to identify food, basically. So let me just close that. All right. You can probably realize I'm not editing this. This is just recorded live. So yeah, whatever happens, happens. Yeah. So we are using the Food 101 standard database. It's a database of, I think, 101 classes of food and about 7,500 training images for each class. So that's 75,000-ish training images and 25,000-ish testing images. And for those who don't know the concept of why we have different training and different testing images, is this fun way that I like to remember it is whenever you're training a model, it's the syllabus on which you're trying to prepare for an exam, and the testing images is the exam. So if you give the same training images as the exam, it's kind of like cheating. The model knows the paper beforehand and it performs. It's not a very fair comparison or fair evaluation of how your model really performs. So you give this testing images or images which it hasn't never seen before, and it'll perform the best it can, and you'll get a fair estimate of how your model performs. So this is how uh, I remember it. It's like you don't want to leak your question paper, right? So it's a nice analogy that you could probably use. So in this model, I've also tried to use some mixed learning. I will come to explain to that in a minute. I will also try to put in timestamps in this video. So if you want to, you can feel free to skip ahead to the specific part which I'm talking about. So the goal at the end of this whole project for me was to beat this food paper, the DeepFood paper. This was a paper I think back in 2016. Let's just wait for that to load. So it was by some Chinese. So these people, some Chinese, I guess, I don't know, American or Chinese. It says University of Massachusetts. All right, they're American researchers. So they have written a paper describing different models, and they try to do this computer vision on this database. So their result, which if I go through a little bit, they got a result of 77%, I think, somewhere here. Yep, they got a top one accuracy of 77.4%. So now our goal is basically to beat that. And of course, this is going to be, it might sound a little bit very complicated, but it's not. This paper was written in 2016, that's over 5 years ago. And technology has advanced so fast that I am now able to do it in my home on my laptop. I'm able to beat that model. And I'm going to show you exactly how I did it. So we're going to be using the power of transfer learning by incorporating the efficient NetX architecture. So for those who don't know, efficient net is a pre-built model. It's one of the top classification models right now out there, and EfficientNet is trained also on the ImageNet, I think, which is similar to the Food 101 database. So I'm hoping it's gonna have some of the patterns already memorized in itself. So that was the idea. So first we're gonna do some feature extraction, and then we're gonna do some fine tuning. So first thing what you have to do is check for the right GPU, because computer vision involves a lot of processing and you're gonna need a GPU to do that. Now I do not have a GPU. I'm doing this on my laptop, but for those people like me, you can use Google Colab. So you can just simply put this command in Google Colab, and it will tell you what kind of GPU you're connected to. And if you don't know how to connect to a GPU, then you can just click on runtime, and you can change your runtime, and it says GPU over there. Now, for this particular process, we're going to be using mixed learning, and mixed learning is only compatible on one of the NVIDIA's free GPUs on Google Colab. So Google Colab provides K80s, P100s, and a Tesla T4. However, only Tesla T4 is compatible. Now, this is because and a mixed learning is only compatible on an NVIDIA GPU with a compute score of 7 plus, which only Tesla T4 happens. So, how do I know that? You can just Google it, you can just find it out, and it'll also give you a small reminder when you come to mixed learning. I'll show you that. So next, we're going to import TensorFlow. We got 2.4.1. Actually, this was supposed to be 2.5 when I first did it, but there was a known bug with TensorFlow 2.5 that doesn't work with mixed learning. So I tried to downgrade it to 2.4.1 just to make it work. All right. So we're going to be importing the raw data. I just imported it from my GitHub right here. You can also check out this. It's github.com/realnihal. So it's called FoodVision using TensorFlow, and you'll find the data set right here, right? You can just copy this and you can paste it in here, and you can find all of the details of the project here and also in this article. So we're gonna be importing the data, and we're gonna download Food 101 from TensorFlow datasets. Now these are some helper functions which I'm importing. So basically, there's some shorthand code which I use quite frequently. So I just put it in there. So I'm gonna just download Food 101, and I'm gonna explore Food 101. There's some normal data and science string things that you do when you get new data. So this is the kind of shape that you get the image in. These are all pretty much numbers, and you can see it's not normalized at all. So we're probably gonna have to normalize it. So yeah, so we're gonna plot one image. It's a club sandwich, and we're gonna pre-process our data. Now, this is a very important step, and this is something where I spent most of my time. So first, we need to be reshaping our images to a standard size. So that's 255, 255. You can reshape it to any size, but this is an industry standard, as it's the smallest size which you can get to without losing much of the important features in it. So if you go more smaller than this, you might be actually compromising with your efficiency, and that's not something that you want. So be careful with this. 255 should be fine. Converting our images to float 32. So yeah, if you see here, all of these are unsigned integers. Unsigned integers are fine. You can work with them, but they're not very efficient, right? So for TensorFlow particularly, float 32 or float 16 are the most efficient. And we're going to look at using float 16 later on in mixed learning. So we're going to try and convert everything to float 32. And then we're going to have to shuffle them again just to make sure that we have a random sample and nothing is, just to make sure. And we have to shuffle them in batches to ensure we don't run out of memory. So if you try to shuffle them all at the same time, we might run out of memory. And since this is not a supercomputer and I'm running it on Colab, we have limited resources. So I written some code to do all of that. And then later on, after we do this, we can see that we have our float 32. And we haven't normalized our functions yet. And there's a reason why I did not normalize that. All right. So next I'm going to be, I'll let you know what the reason is later. So next we are going to be mapping our pre-processing functions to training data. So this is our training data. We're going to just map our function. So this is basically a function that will take our images from a file and try and process it into our model. So this is like a pipeline of sorts, a data pipeline. So tf.data.autotune. This is important here because what this does is it it ensures this process is completed in parallel with all of the CPU cores that you have. So by default, any Python function or Colab in general, it performs any sort of function that you have on a single CPU core. Now we have multiple cores in your computer. You could take advantage of this if you know what you're doing. And here, if I was to use a single core, this would take ages to load all of the images one by one into our model, and it's going to take ages to train. So to reduce our time, I'm going to use this auto tune, which is basically going to put some parallel calls to all of our cores. And in Colab, I think we have two cores available. On your, if you're using it on your PC, you might have multiple cores. So if I was on a laptop, I would have four cores or something. So yeah, you could do that if you want. The same thing with our shuffling of our data. So we're gonna have a buffer size of 1,000. I just told you why. So the same thing with the test data and all. So we get a prefetch dataset, which is basically a function which fetches your dataset when called upon. So yeah, next we're gonna come to the main part, which is implementing mixed precision. So what is mixed precision? This is supposed to be float. Okay, I'll try to change that in my own time. So here we basically converted, if you remember, we converted all of our numbers into float 32. Now, to improve efficiency, we could try and convert some of them into a float 16. And this is only compatible with GPUs with a compute score of 7 plus. So if you do a set global policy, we can see your GPU will likely run because it has a compute capability of 7 plus, it says. So you get this thing just to make sure. So yeah. So now we have next implementing mixed learning on. We're going to define a feature extraction model. So we're going to have an input layer, an efficient NP0, a pooling layer, and an output layer. So we're going to try and ensure that most of it is freezed. So if during feature extraction, you would only want the outermost layer to be separate and everything else to be freezed. So you just want to implement that last layer and you want to train that last layer in a way. So we have our input layer, it's just the base model, the global average pooling, the tens layer, and this is our output layer basically at the end. So these, essentially, most of the learning that we're doing is only going to happen around in these layers. So we're trying to optimize for that. So that's why this is called a feature extraction. We're not trying to actually, do a final learning here. It's just extracting some features. So if we do some model summary, if we see what all are trainable, we can see that only the last couple of layers are trainable, and the efficient net is not trainable. Only the last three layers are trainable, and obviously the input layer is trainable. Next, we had some callback functions. So TensorBoard callback. This is to save our progress on a TensorBoard file. I will share that link too in the description, and it's also there on the article if you want to check it out. There's a model checkpoint. This is just to save the best model. I think I have saved the best model on GitHub. I'm not sure. Yeah, but you can find the best model if you run the code on your own. You could get the Colab or the notebook file. So fitting the data on feature extraction model. Just fitting the data. Got some three. We got to 3 epochs, and the values did not improve from 0.71. So this is 0.71 is less than the DeepFood paper, but this is only half the progress. So we have only done feature extraction till now. We haven't done the fine tuning. So we're gonna just see our results, and we got around 70%. It's close, but it's not beating our target. So let's try some more. So now we're gonna make a fine-tune model. So the basic difference between a feature extraction and fine-tune model is we have an input layer and we have our efficient net, we have our output layers. So efficient net has already learned some of the features from its training on ImageNet and like hundreds of other models. So if you just type in efficient net, we can see something. Yeah. So this is an efficient net. Uh, Yeah, my laptop is kind of slow when I try to record it on OBS. All right, so this is an efficient net. It's highly accurate and for a less number of parameters, and it's really good. And it's trained on hundreds of data sets, and it has learned a lot of the models. So we do not want to be retraining that. So we don't want to reset all of that learning. So we're going to fix the learning on the efficient net, and we're going to only switch on learning on the input and the output. This is the feature extraction phase. So now after this phase is done, the model sort of understands how to use the efficient net in a way. So now we're going to go to fine tuning. Fine tuning is when we're going to allow training on the last few layers of the efficient net. So this will allow our outermost layer and the efficient net to kind of understand each other better, to have to have more of those features extracted in the efficient net, making it through to our final classification on the outermost layer. I hope you get what I mean, but if you still didn't get it, there's always you can read through the article. There's a lot, I've written a lot about it, and you can understand quite a bit. So, viewing the results and saving a fine-tuning model. So basically, that's what I did. We opened up some of the input layers to be able to be trainable, and then we retrained our model. Then we saved our model, and then we're gonna view our results, and we get a score of 78.3. Wow. Now this, obviously, I know the result of this before. Uh, but yes, we were able to beat DeepFood's paper, and it's not a surprise. I mean, 5 years is a long time in technology, and we've come a long way. And I was able to beat some top researchers and their paper. So yeah, it's a little bit of a laugh there. So yeah, you can. There's a link to this analysis on TensorBoard. You could check it out. Um, I'm just gonna yeah. So you could check out the TensorBoard analysis later on if you wish. So this is the conclusions. We found that yeah, the efficient net model is trained on the ImageNet, so there's slight overfitting because of that reason. And the images also, ImageNet consists of food images as well, like say similar to the Food 101. So that's one of the reasons why there might be a little bit of overfitting and why we did not go beyond 78% or where we didn't go into the 80%. So if you try to solve, if you're able to solve that issue, we might get our model to go into the 80s, 80%, 85%, possibly close to 90%. Can't really say. So, but anyway, we have achieved our objective. And if you see our TensorFlow callback, so this is some interesting data. If you would like to look into my specific training and you wanted to see what all happened, you can. This link will be there in the description. It will be there in the article. You can go check it out. And do follow me on Instagram, do follow me on YouTube, subscribe, like. Please check out my blog, and I'm gonna try and upload quite frequently, so that there's some cool content for you guys, and even I stay motivated and continue on my journey of learning. And with that, I guess that's it, and peace out.